Today, after working here at STEMinar Lab, I went on to work at a different laboratory, which is called CERN, which is located near Geneva, and I'm going to talk about some of the things that are happening there. So the outline of my talk, first I'll talk about particle physics to give you an idea of what we do there. And then before talking of all the people working at CERN, I'll just say a few words about diversity in physics, because it's still quite a niche for selected people or whatever. And so then I'll talk about how do we manage to achieve what may seem impossible, discovering these tiny particles, and how do we work, which is something most of you are probably in the engineering programs. Am I correct about that? Are there other majors here, others than engineering? So we have lots of engineers at CERN, and you see the model that we have to operate can be used also in other places where you will work, and you see it's quite nice. And all that we do is to find absolutely useless particles, and I'll talk about that, and then why do we do it, and what is left to do for those who could be interested in looking into that. So what is the aim of particle physics? Particle physics is there to find the smallest building blocks of building blocks of matter. So we're trying to figure out what are the smallest grains of matter. If we were in Copenhagen, in Denmark, where Lego blocks were invented, then it would be easy to figure out what are the smallest building blocks of matter, because there everything is built with Lego blocks like this. And then it would be easy if someone was to ask me what are the smallest possible grains of matter we get, then I would just shatter one of the exhibits and I would get all the fundamental particles that exist at Legoland. Those are the ones that we cannot break any smaller. Okay? Those are the smallest ones that we find, those that we call the fundamental particles. And with them, you can build everything else. Matter, regular matter, everything that we see around us, it also is also built like something made at Legoland with small building blocks that we reuse and make everything with that. So what are the smallest particles that we have in regular matter? So if I take a block of wood, for example, and I try to look what is inside, you know that there are atoms there. But atoms are really, really small. An atom is about 1 million times smaller than a hair. Here's a picture of one individual atom. It's the smallest object that has ever been photographed. And it was done with some quantum microscope, something very precise. So 1 million times smaller than a hair. If I go in a metric unit, then it's 10 to the minus 10 meters. 10 to the minus 10, you know the scientific notation. It's not a problem for you. OK, everybody's familiar with that. So it's very small. But it's not the smallest things. Atoms are not the smallest units that you find inside matter. It's inside the atom, you also have the nucleus. And the nucleus is 10,000 times smaller than the atoms. But inside the nucleus, we now know that there are protons and neutrons. And those, inside the protons and the neutrons, that's where you find quarks. And the quarks, we don't even know how small they are. They're smaller than 10 to the minus 19 meters. So it's very, very tiny. So it's difficult for us to understand that regular matter is built just like anything that we build with Lego blocks. You take the smallest one and you build everything with that. But that's what I'm going to show you. So on this picture, if I ask you, what are the smallest particles that we cannot break into anything any smaller? Quarks? Yeah? Anything else? OK. I'll ask an expert. electrons. Electrons, you cannot also break them any smaller. So the only fundamental particles here are electrons and quarks. And here is how we can build everything that we see around us, all the material world, including ourselves, with quarks and electrons. To make protons and neutrons, we need, in fact, up and down quarks. And up quarks have an electric charge of 2/3 of the charge of an electron, but it's positive. And a down quark has an electric charge of -1/3, so 1/3 of the charge of the electron and negative. And you see, I can take 2 up quark and 1 down quark, and with that, I get 1 proton. And that's as much mathematics that we have here tonight. So plus 2/3, plus 2/3, together it's 4/3, minus 1/3. Then you get a proton, which is a particle, a composite particle that is electrically charged with a positive charge. And to make a neutron, a neutral particle with up and down quarks, can you see a way to do that? Maybe, maybe not. With 1 up quark and 2 down quarks, you see, I get a neutral particle, and that's the neutron. So now I can assemble up quarks and down quarks together to get protons and neutrons. Then I can assemble protons and neutrons in different proportions, and I can reproduce all of the periodic table here. The lightest element is hydrogen. In the hydrogen, have 1 proton with 1 electron around. The second one is helium, and the difference is just that instead of 1 proton, I have 2 protons, and this one has also 2 neutrons. The third one is lithium, and then you have 3 protons. So from one element to the next one, all you have is that you add 1 more proton, and you get different chemical properties. And in an atom, you always put the same number of protons, same number of electrons around as you have in the nucleus. So if you have 5 protons, you put 5 electrons, and that gives you 5 is a boron, B there. And you also put some neutrons in the nucleus just to keep the whole thing stable. So with up quarks and down quark, I can make all the elements in the periodic table. And you know that those elements, with that, you can reproduce everything that we see around us. Not only here on Earth, but also everything that is around us in stars and galaxies. Because you know, when you heat up something, like when you heat up a piece of metal, it starts glowing. Any element that you heat up will start emitting a light, and it has special colors, special spectral lines, we call them. And so we can identify the elements from the light that they emit when they are heated up. And so we know that by observing the light coming from all the stars and galaxies, we know that they're all made of different elements that we have in the periodic table. So everything we have around us in the universe is made of up quarks, down quarks, and electrons. Okay? So in the 60s, things were really complex. We were finding lots of particles, and it was quite difficult to figure out where they were coming from. But now we know we have a model that explains what matter is made of. And this model is called the Standard Model, and it has 2 basic principles. The first one is that all matter is made of fundamental particles. Just like at Legoland, everything is built out of a series of Lego bricks. So we have, in fact, 12 building blocks, and they come in 2 different families. They are the leptons that you see on the left, and the quarks on the other side. So in the lepton side, I already mentioned the electrons. We can have also the muon. The muon is similar to an electron, but it's about 200 times heavier. And we receive muons sometimes from cosmic rays. And tau particles are about 4,000 times heavier than an electron, but they behave quite the same. They also have an electric charge of -1, like an electron. And those three particles, they all come with a neutrino. And neutrinos are, I brought one of them here, the tau neutrino. Neutrinos are very special particles. They barely interact with matter. So there are millions and billions of neutrinos coming from the sun and passing through this room as we speak, and they don't even stop to say hello. You know? They can go through matter without stopping. And I brought one of them just to prove to you that they exist. So I'm going to pass them around. So here is a tau neutrino. Those are there was a young seamstress. She came to a public lecture like that, and she heard about those particles, and she thought it was quite funny. So she started making them, and she has the whole zoo of the particle zoo, and she's the zookeeper now. So you can find all the particles on her website there. So there are two families. The families like Gagnon, and they are leptons. So that's just a family name. And the other family is made of quarks, and we call this family hadron. Hadron, the name will come back later. So any particle that is built out of quarks, we say that it belongs to the family of hadrons. So the quarks, I already mentioned up and down, but we also have the charm and strange quarks. The first one that was found was the strange. They were particles that had a very strange long lifetime. And all those particles turned out to have this special quark. And people gave him the name of strange quark because it had a strange behavior. And the next one was called charm. Why not? You know, you had a strange one, you had a charm one. And the last two were initially called truth and beauty, but then people thought, okay, that's too much. We stopped fooling around. And it came back, and they're rather known as top and bottom. And the top particle was found here at Fermi Lab, 1990. No, I was in Ottawa at the time. 95, that's it. Yeah, I was in Ottawa at the time. And the top quark, which is the heaviest of all particles that has been found, and the bottom quark. So bottom quark was also found at Fermi by Leon Lederman and strange quark. Maybe charm quark was at SLAC in California, and Brookhaven. That's true. Okay, so here is all the building blocks that we have, and with all the particles that exist. And what is really strange is that it's like a construction set, you know, and those are all the parts that exist. But it's a very strange construction set for many reasons. First of all, it's like I give you at Christmas time a construction set, but some of the pieces are big like this, and others are big like that. So they're very disproportionate in size. So it's a strange construction set. The other thing that is weird is that we only need the first row of those particles to build all the matter that we see around us. The other ones are useless. So imagine that I give you that as a gift at Christmas, that I give you this construction set, but there are all sorts of pieces that are not used in anything. So it's a strange construction set that we inherited. So we don't know why those other particles are there. We can produce them with particle accelerators like we had here at Fermi Lab or at CERN. Or sometimes we see them in a very energetic processes that take place in outer space. Well, we mostly receive muons here. The other particles are much more rare. So our model that explains what matter is made of is called the Standard Model. The first principle says everything, all matter is made of those fundamental particles. The second principle is that all those particles, they interact with each other by exchanging bosons. And those exchange particles are called bosons, and they are associated to the 5 fundamental forces that we know. And it's like, so imagine that the grains of matter are like those little beads here, And some construction sets, you might have seen some of them, they come with connectors. So like this here. I can connect the grains of matter with a connector here in between. So those bosons, they act like the connectors here that bind things together. Except that it's not static, something rigid like this, but rather an exchange. So they toss particles at each other. I'll come back to that in a second. But there are 5 fundamental forces. The strong interaction, that's the one that keeps the quarks bound together inside a proton or a neutron. And that's done by exchanging gluons. Then there is the electromagnetic force. And this one comes with a particle called the photon. This one is a massless particle. I'm going to send it to you, sorry. There goes the photon. And so the photon is a massless particle, and it's associated with the electromagnetic force. The weak interaction is what takes place on the sun, and that is responsible for radioactive processes, for example. And there are 3 particles associated with that, 2 Ws, one that is positive, one that is negative, and the Z boson. Finally, we have the graviton, but that one we don't know if it exists or not. The graviton has not been found. You might have heard that we have found that scientists have found gravitational waves recently, and this discovery was rewarded by a Nobel Prize in November. No, it was not in November this year. Anyway, so they just got it a few weeks ago for the discovery of gravitational waves. But we think all the waves that we know, they come with a particle that is associated with it. But we haven't found the graviton yet. We might find it, but so that's why there is a question mark there. And the last one is the Higgs boson. And that one was just recently found in 2012 at CERN, near Geneva. So here's my Higgs boson. So, whoa. And this one is the particle that is related to a mechanism that gives mass to all the other particles. So you see, that one is very heavy, contrary to the photon that has no mass. So how does it work, this exchange of particles? So imagine that you have 2 skaters here, and they're moving along on their own trajectory. And imagine that they toss a heavy ball to one tosses heavy ball to the other one, and then it will make them diverge from their trajectory, as if there was a force that had acted on them that made them change their direction. But it's not an action at a distance. It's because one of them tossed a heavy snowball at the other that made them diverge from their trajectory. So the one that tosses something recoils, the other one catches it and also recoils from it. So the exchange of particles, that's the way the forces, the interactions take place by exchanging the particles that are associated with the force, which we call bosons. So we had a better understanding with the standard model. We had a better understanding of how it was going, but nobody had an idea on how those particles could get their mass. And that's when these theorists came by, and they all added a piece of information that now give us a much better idea. The first 2 that did something were François Englert and Robert Brout. They were 2 Belgian scientists working together. And they were the first one to propose a mechanism to explain how particles acquire their mass. And they realized that this implied the existence of a new field of force, and that particles acquire their mass by interacting with this field. I'm going to go over that step by step in a second. But the first 2 were these 2 guys. But most people know Peter Higgs much better because there is the Higgs boson. And Peter Higgs, in fact, published his article a month after the other ones. First, he had submitted his paper to a journal, but it was refused. And the editor said, it's completely useless, your paper. You don't have any specific predictions with that. Then he was really bummed out that it was turned down. So the next time that he resubmitted this paper to another editor, and this time he said, yes, but don't forget that it comes with a new boson. So he was the first one to predict the existence of a boson. That's why the Higgs boson is named after him. And in 2013, both François Englert and Peter Higgs got the Nobel Prize for predicting the existence of the Higgs boson. Robert Brout was already dead, so Nobel Prize is unfortunately given only to living people, so his name wasn't there. So what, and the other ones, the other three guys here were people who completed the theory, in fact. So lots of people were involved in discovering this mechanism. So what they said was they realized that there was a new field of force. And what is a field in physics? It has nothing to do with something like that. It's more like it's something that modifies the property of the space around it. So if we have a magnet, for example, and we were going to put iron filing around it, all the little grains of iron will just go and distribute themselves along the lines of force, of magnetic force. So when you have a magnet, you don't see the lines of the magnetic field around it. But if you put something that is sensitive to this field, like iron filing, they will behave differently around this magnet. So a field is something that changes the property of space around it. So like a magnetic field, for example. So I'm just going to introduce a few concepts before we go further. So what is mass? Mass in physics is resistance to motion or to the change of the state of motion. Like if you have a huge boat like this, to put it in motion takes a lot of energy, and to stop it, the same thing, because the boat has a huge mass. And in physics, energy and mass are equivalent. You all know this equation, E equals mc squared. You've all seen that? Yeah? Who wrote that equation? Einstein? He was not alone. Everything he did was with his wife at this time. Yeah, and it's absolutely unknown. And I have this story on my book, but it's also, you can find about Mileva, Maric, Einstein. And for 18 years, they worked together. And everything that they did, photoelectric effect, E equals mc squared, special relativity, all that was done together. So E equals mc squared, what does it say? It says that energy and mass are two forms of the same essence. Just like right now, I'm Canadian, so I have Canadian dollars in my wallet as well as American dollars. And those are two forms, two currencies, but they're two forms, different forms from money. And there is an exchange rate that exists between the two. Between energy and mass, it's the same thing. So energy, you can look at mass as being congealed energy. And there is an exchange rate between the two, which is the square of the speed of light, the c square, the square of the speed of light. So you can take energy and condense it or congeal it, and you will get some mass. Or you can, and that's what we do with the particle accelerators. Come back to that in a minute. And then, or you can, in a nuclear reactor, you can take matter, mass, and blow it apart and extract the energy out of it. So E equals mc squared. And the last thing is that the energy conservation. Energy can take several forms, like kinetic energy associated to movement. But for a fundamental particle, it can also take, you can also have energy, congealed energy, in the form of mass. So it's like if I had these containers there were just containers and have a liquid, the red liquid, and I can pour it. If I have this amount of energy here, I can put it partly in the kinetic energy container associated to movement, or some in the mass container. But the sum of the two, the quantity of liquid that I have, must always be conserved. So with that, let me show you how it works to give, how the fundamental particles can acquire their mass. If we were in a space here without any field, this new field that is called the Brout-Englert-Higgs field, if there was an empty space without this field, then a particle that is at point A could go to point B at the speed of light. Okay, we'll do it more slowly. It could go from A to B on a straight line, moving at the speed of light. Nothing would slow it down. But, so at this time, all its energy in the form of kinetic energy associated to its movement. But something happened right after the Big Bang. Someone turned on the Brout-Englert-Higgs field. That happened something like 10 to the minus 25 seconds after the Big Bang, something like that. And then it is as if this field was everywhere in space, and then a particle that is trying to go from A to B starts interacting with the space around it. Okay? It is as if I'm trying to run, and if I run in a schoolyard and there is nobody there, I can go at full speed. But imagine that there are lots of kids in the schoolyard and I try to run. I'm starting to interact with everyone, you know. I'll bump into everybody and I will be slowed down. So you see on this case here, the particle has much less energy associated, kinetic energy associated to its movement. Where did the rest go? It cannot lose energy. There is energy conservation, so the energy appears in the form of mass. Ta-da! So it's the small miracle that happens with the Brout-Englert-Higgs field. It's a field that is non-dissipative, so you don't lose energy. You just change the format in which you find it. So by interacting with the field, some of the particle's energy is transformed into mass. So we have a field. We have particles interacting with this field that gives them mass. So what is the role of the Higgs boson in that? So the Higgs boson we could compare the surface of the ocean to this field. And the Higgs boson would be like a wave at the surface of this ocean. You know that you can excite the ocean to create a wave. The same way we can excite the Brout-Englert-Higgs field and create a Higgs boson. So the Higgs boson is, waves are excitations of the ocean surface, and we can create Higgs bosons by exciting the Brout-Englert-Higgs field. So what we did, how did we do that? We had a massive particle accelerator that brought a lot of energy in a tiny, tiny point of space, and it just excited like the canvas of the universe, and we got that wave, which was the Higgs boson. Okay, so before coming back to that, let me say a few words about where was the Higgs boson found. So that was done at CERN, which is the European Laboratory for Particle Physics. That's a place where we have 12,000 researchers coming from 63 countries. So there are 63 countries around the world sending researchers to work there. It was founded in 1954 by UNESCO, and it was just a few years after the end of the Second World War, and it was a means to bring back peace in Europe. And it's financed by its 22 member states. The member states are mostly Europe, that's the way it started. But now they are opening their door to other people, and recently there is Israel that joined, and there are other countries that are in the process of joining, like Pakistan and India, and others are in the process of joining. And so those are the ones that are in the process of becoming official members. And you also have not only the member states, but you also have observers, like in the United States is one of those countries. And there are also users, countries that only send people to work there without participating in the decisions and all that. So on the map here, everything that you see in blue, the countries you see in blue are member states. The countries that you see in green are observers, so they can at least attend the meetings and see what kind of decisions are made. And the others are just users. Like Canada is one of those, lots of countries in South America, Australia, more and more countries in Africa are joining and all that. So, and for example, the USA sends 1,900 researchers, physicists and engineers to work there at CERN. But in fact, like myself, I'm Canadian, like I said, but I was working for an American institute. So if we look at people by nationality, then you find 1,100 American scientists. So it means that American institute hire people from other countries as well, like it was my case. And then you see that there are 102 nationalities that are represented at CERN. So 63 countries send people, but we hire physicists coming from all over the place. And if you had come to a major meeting of physicists 100 years ago, that's probably what it would have looked like this famous picture from the Solvay conference. It was a conference in France in 1919. So there are a few people that you might recognize here. So Albert Einstein is here, Marie Curie. And the other ones, I know several names, but I don't know the faces. Niels Bohr and Heisenberg and all those people were there. So you see that it was mostly, almost uniquely, white men who were there. But if you come to CERN today, that's more likely the kind of crowd that you will meet, those who are participants in a summer school, for example. But diversity is not quite yet achieved at CERN. For example, here is the distribution of the people. So you can see, because it's a European lab at the start, so you can see that most of the people, 3/4, come from Europe. And we have about 18% of women in total. So, and from Asia, there are about 13% of the people come from Asia, and that's mostly India. There are 11% of the scientists, of the 12,000 scientists working at CERN, come from North America, so that's Canada, in case you don't know, Canada, America, USA, and Mexico. And then very small, South America, Africa, and Oceania. So right now at CERN, we have roughly 80% of our scientists are male and 80% are white. So we have more diversity, but more diversity than a century ago, but it's still not completely achieved. And if we look at the age of people, and if we were to look at the people under the age of 35, to see how it might evolve in the next few years. But you see, Asia is going to take a bit more space because there are lots of young Indians there. But it's not going to change by very much. So we might achieve 23% of women. So we need to do a bit more to really achieve diversity there. And it's a big problem. And I just want to say a few words about diversity here. And nobody has been able to establish the superiority of white people over other races, or the superiority of men over women. There's no test that has ever proven that. And in fact, in all my career, I spent 19 years at CERN. I've never seen a man using his genitals to solve a physics problem. So, you know, it has nothing to do with that, and it has nothing to do with gender or with race or with sexual orientation. It only has to do with, it's an old social and political problem. But the old ideas prevail, and many people don't feel quite accepted there. So the stereotypes need to be addressed. People who are members of the majority group, white men, don't always know that how it could be for others. So it's really important to have those discussions. And within the minority group, we must fight the stereotypes that are often internalized. There's one classroom experience that really helps women, bringing more women into physics. And this experience is the explicit discussion of why there are less women, fewer women in science than men. Then women can realize that the problem doesn't come from us, from being inadequate or anything, but it's just all stereotypes that are perpetuated all the time. So there's nothing wrong with us. We're just as smart, and black people, Asians, everybody is just equal. There's nothing that makes a difference. So this is the classroom experience that really made a difference, that when you realize that it's not a personal problem, but a social problem. And many women have experienced this thing, and everything that I say for women applies to any other minority. That when you're constantly told, like myself, I don't know how often people ask me, why are you in science? No, like as if there was something wrong with me, whereas men are not so often asked this question. And for women, it's a well-known fact that many women feel the imposter syndrome, and it describes very highly successful women who have difficulty internally recognizing their own achievements. These women believe that if they made it in the field, it's not because they were equally smart, but simply because they worked harder. And many women will think that, for example, the kind of thinking that goes along that, women would say, sometimes I'm afraid others will discover how much knowledge or ability I lack. And most women will have experienced that. Or they would say the major cause of a success in my life is my high ability. Very few women will think that. And I feel highly confident that I will succeed in my future career. And again, most women don't feel that. And we kind of make it fearing that one day someone will find out about us. And this is a common thing. Once you know that many women experience that, then you stop thinking that it's your problem, but it's a problem of being a member of a minority group in a majority group. So it's good to think about that. And one other thing that is good to know is something that is called the stereotype threat. If you give an exam to students and you enter the classroom saying, it's well known that Asians do terribly on that test, on those math tests, and then you pass your exam copies around, you can be sure that the Asians will underperform. Because of this, it's called the stereotype threat, you get influenced by those ideas. And likewise, if you walk into the classroom and you say, it's well known that white guys do really well on those tests, then those will overperform. And if you don't say anything and just pass the copies around, you won't find any difference between black or white students or male or female or anything like that. So it's good to know those things, and then you know that there's nothing wrong with you and we can all do it if we work hard at it. So all that to say that at CERN we have very large collaborations. Here is a picture of the CMS detector and some of the 3,000 scientists that we're working on them. So we have about 90% of physicists, but there are about 10% of engineers among them as well. So there are 4 large experiments that are now operating on the Large Hadron Collider, the LHC. And those are called ATLAS, that's where I work, CMS, LHCb, and ALICE. So what we have is a huge tunnel We don't see it like you see a ring around the Fermi Lab because they have some services at the surface. But at CERN, we don't see that ring. So if you come on the plane, you will, here is the airport in Geneva. You see Lake Geneva there and the Alps in the background. And this ring here makes 27 kilometers. 27 kilometers, that's something like 27, about 20 miles. 20 or 18 miles around. So it's a huge thing. That's why we call it large. The Large Hadron, because we put proton inside, so particles made of quarks, collider, because we make them collide together. So we don't see this ring because, in fact, it's underground. It's 100 meters, like 300 feet underground. We find this accelerator. The accelerator is, in fact, a vacuum pipe with big magnets around it. And we use electromagnetic waves to accelerate the particles around. And we use the huge magnets, they're superconducting magnets. We use them to bend the trajectories of those particles to keep them spinning on a circle. And there are 4 caverns that were excavated at different points. They're huge caverns, and it's inside there we have put our detectors. So to do particle physics, we have 2 major tools. We have an accelerator, which accelerates particles, and it will bring them at high speed and then bring them into collision. So you will have protons colliding with other protons right in the center of a detector, which is like a huge camera that will take pictures of all the things that will come out of there. So how it goes is that the energy released during the collision, so we take the protons, they collide together, and the energy that is released in this collision materialize in the form of new particles. These particles are highly unstable. They will break apart, and it gives mini firework. Again, smaller particles flying in all directions. And we put our detectors, they're built like cylinders, several layers, and with end pieces like that. So it looks like a big can, a tin can. So a cylinder with 2 ends, and you put several layers of your detector. Each layer has a different function. We'll see that in a second. And we try to catch all the debris that will come out of there. So we produce those mini fireworks, we catch all the particles, and then we try to reconstruct which particle was produced in the first place. So here is a small film to show you how it goes. So we start by accelerating protons in a small accelerator, which is fairly small, 157 meters. Then we inject them in a larger one, and then they gain more energy. Finally, they get in this one, which is 7 kilometers around. And then they gain, again, more and more energy. Finally, they get in the Large Hadron Collider, and they reached the maximum energy of 7 tera-electron-volt. So we see the protons now are being accelerated in that large vacuum tube. We see the quarks inside the protons. And this proton is coming from one direction. In fact, there are 20 billion bundles of protons coming in one direction, like a swarm of bees in one side, another swarm on the other side. And then some of them will collide, create new particles. And we have our detectors that are built around them to catch all the particles that comes out. Okay. Okay, so the detectors are made of several layers. It looks like an onion. Okay, several layers, one on top of the other. And some of those layers are there to reconstruct the tracks, the trajectories of all those particles. And others are there to measure how much energy each fragment had. And with that, we can reconstruct what was produced at the beginning. And we take pictures. Well, in fact, we record all sorts of signals with the electronics. And with that, we can reconstruct a picture of what happened. So what you see here in the center, I told you there are about 20 billion protons coming in one side and 20 billion from the other side. And then they collide in one point. So some of the protons will make head-on collisions. And then there is a lot of energy release. And when those particles that were formed at very high energy, they will be heavier particles. They will break apart. They will give fragments that will fly at very high speed. Others will just be grazing each other. Okay? Like imagine two swarms of bees. Some will make head-on collisions, and others will just barely touch each other. And then you get small particles that are created, but they don't have much energy, and they just curl around because we have those strong magnets there. So everything that has an electric charge will just curl around. So we take pictures, and we try to reconstruct what happened there. This particular event could have been from a Higgs boson. We never know from one picture if this one was a Higgs boson or not, but we take lots of those pictures, and statistically, we can say that, yes, there were some Higgs boson on that. But not on one individual picture. We must take lots of those pictures together. So where do we start to produce those? How do we build those detectors? You know, there are 3,000 of us, and we want to find Higgs boson, or we want to find other particles. How do we proceed to build our detectors? So we start from the theoretical predictions. And so theorists will tell us, oh, if you have gluons attached in the protons on each side, and gluons coming here, gluons coming there, and then they interact, and they could fuse and give a Higgs boson, and they would give top quarks. And so you see, they predict that we will get all sorts of particles coming out of there. So there would be big quarks and neutrinos and leptons and all sorts of things. So we build our detectors such that they would be sensitive to a variety of particles. There's only a handful of stable particles that will be found in our detectors, so it's not too difficult. We make several different layers, and each of them will be able to identify some of them. And since these particles will fly in all directions, we want also to be and they might be sometimes really close to each other. We want that our detectors will have high granularity. Other possibilities that the theorists were telling us was that quarks coming from the two different protons entering in a collision would exchange some Z boson or W boson, and those would fuse and give us a Higgs boson and some quarks. So you see, we would see the initial quark would just barely deviate and continue in the same direction. So we need to be able to measure things in all possible directions. And our detector must be fast and precise. And they were also predicting things like supersymmetry. And that's a theory where the two families of not only the grains of matters, but the bosons, they mix together and give something that has a bit more symmetry. And in that case, a supersymmetric particle would always decay in a supersymmetric one until you hit the lightest one, and that one will escape the detector without interacting. So we want a detector that is absolutely hermetic, such that no particle would escape. And we can measure how much energy we should find together in all directions, and then we can see if something escaped. We know the total energy that should be found, and if something is missing, then we would know that something has escaped. So the detector must be very hermetic. So the way that we do that, the first step is by the collaboration. The 3,000 people decide together what kind of detectors do we need. So we would want a layer that would find photons, that would find electrons, that would be able to get the tracks of all the particles that escape with a charge. And then we'll get to an agreement of what kind of a project we would need. And the whole project would be divided in smaller projects. So we need a calorimeter, we need a tracker, we need different things. And then each institute that wants to participate in that experiment, we say, well, we'll take care of this part of the project. So we divide the project between all the participants. And sometimes two groups will say, oh, I would be interested in trying to do that. And they will have different ideas on how to do it. And they will pursue ideas together in parallel. So we spend lots of time discussing with each other. And everyone can suggest ideas and how they would like to do it. And each people or each group that suggests an idea must prove that what we are doing is really the best way to do it. So we do it not using alternative facts, but we do it by showing proofs that we have measured this and that with a prototype, and we can do that, and it's possible. So we have this huge project that we want to do. We divide it in projects, and sometimes two groups work on the same thing, but they must always prove which one has the best idea. And the best method is selected on its merit, and the common goal has to prevail. It's not because I decide that it's better. No, I must prove it. And there is no chief that is there saying, I'm the boss, and that's the idea. There are only coordinators that will get the whole project going. And even when the coordinator disagrees, if you can prove that it's better and that everybody agrees on that, then that's what we will do. So there's no top-down hierarchy. There's no director, only coordinators. So everything is discussed in meetings, and we spend countless hours in meetings. And so everybody brings their laptop and keep working on other things in parallel. And everyone chooses to do what they want to contribute to the project. Everyone does as they please. It's a bit like you make a huge picnic, and you tell people, bring a dish. And you might say, oh, I'm good with potato salad. So you'll bring potato salad. You said, oh, I'm not so good, I can bring beer. And everybody will propose different things. And I can be there coordinating to make sure that there will be enough to eat and enough to drink and not too many desserts and enough main course. So we just work like this. Each group volunteers for a task based on their tastes and resources and the needs of the experiment. Each person must figure out how to contribute to make sure the whole project is successful. So we're all responsible. And I was working in a group where there were people who were highly unpleasant, you know. And we were all doing the same task, and they didn't manage to finish their part of the project. I finished. But I cannot just sit there and say, nya, 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 nya. No, I have to go and help them, because if they don't finish their part of the project, the whole project is a failure. So we must always collaborate together. And how do we motivate ourselves? So the common goal is to increase human knowledge. We want to find if there is a Higgs boson. We want to find if there is supersymmetry or new particles. So that's the common goal that we have. We just want to bring more scientific knowledge. But there are no bonus. The only benefits for the individual benefits is that we get to participate in very interesting projects and maybe get some of the answers to the questions that we have in science. But even if I finish my project in time and all that, I won't get a financial bonus. We only do it because we're self-motivated. We want to get answers to our get better answers, to understand why there are all those useless particles in the construction set. Why do we only use some of them? Why are the masses so different? all sorts of questions that we still have no answers. So, and that's good to work like this, where everybody does as they please, because then the creativity is not blocked. Everybody will give their best trying to get this project to be a success. And we need the creativity of everyone. And so we must collaborate, but we are also in competition with each other, because they are not jobs. We're all postdocs at one point, and we're all competing to get faculty positions, and they're not jobs for everyone. So that's not always easy, because we must collaborate, but at the same time, we're also competing to get a job on the long term. So that's always difficult. But of course, when the project is successful, everybody shares the thing. But the funny thing is that we're all there volunteering to do the toughest jobs. Like, I volunteered to test 110,000 wires. And we had to build very complex things to manage to do that. And we had only 1 year to do it. And it was not obvious. And at the start, that was my experimental setup. I had a tiny power supply and a little bit of gas coming and all that. And then I got an engineer with me. And no, I was the physicist, and then an engineer came. And so about 18 months later, we got it going. But all of us, we had to learn as we were going and all that. And we were forced to give the best out of ourselves. Like here are the hands of my engineer, Kirill, who was a Russian. And when he arrived at CERN, he hardly spoke any English or French. And he had to learn English for the job, French to live in France and near Geneva. But the guy could draw. So when he had to explain something to me, he would make a drawing. And I also learned some Russian. And in the end, we got going. And he was really talented, and he was very creative and came up with all sorts of ideas. This module here is about 4 feet long, and it was little straws that were no bigger than a drinking straw, but this long, with a tiny wire strung in the middle. And sometimes he had to go and retrieve the wires from there, from inside one of those straws. And we had to make sure that they were perfectly centered and all that. So it was a very difficult task, but he came up with all sorts of ideas. But people, always volunteer to do tough job, and some of them can let go. Like Maria and Giuseppe Fidecaro, they are there at CERN since the beginning, since 1954. So Giuseppe got a job right when CERN opened. Maria was with him, and she went to work there too. She was not paid at the beginning. It took her 2 years to get a real job. But they're there since then, and they're still coming every day to work in the lab. They're just passionate, and they want to keep going on their work. And what we do, our detector it's a massive machine. Here is the center part, the calorimeter, the piece that is there to measure the energy of each fragment that flies in the detector. And we have 4,000 kilometers. 4,000 kilometers, it's larger than the size of the United States. So it's 4,000 kilometers of cable. Each cable had to be cut at the right length, fitted with a connector, and connected at the right place. We had to test that everything was okay. We had to make sure that no one was getting there with a ladder on his shoulder and turning the corner a bit too fast, because it's a massive construction site. So you can imagine there are always people carrying large pieces of equipment. So we always had to check that nobody was nicking a cable or something. So 4,000 kilometers of cables, and just as many tubing of all sorts with various gas and cooling liquids and all that. The detector is 7,000, the Atlas detector is 7,000 tons, weighs 7,000 tons. That's the weight of the Eiffel Tower. But the Eiffel Tower, as you know, it's only rusted steel. Here it's just tiny, ultra-precise pieces. Like my friend Monica Dunford likes to say, she says it's like a Swiss watch on steroids. You know, this is a massive instrument, so it's both very, very huge, heavy, industrial type, and at the same time, ultra precise. And it's very tall. The detector was 6-story high. Here's this guy is trying to make a selfie in front of the detector, but I never saw his picture, but I doubt it was really good. So how did we manage to make it work? And the main reason is that we're all highly motivated. People are motivated. This motivation comes from our scientific curiosity. We want to get the answers to our questions. And when it works, well, the success is shared, like here, after the discovery of the Higgs bosons. So those were just a subgroup of all those who were working, trying to find the Higgs boson, and they're popping the champagne bottles there. So why do we bother? Why do we work so hard to make this work? What is the reason behind all that? Because particles like the Higgs boson, they live 10 to the minus 25 seconds. Try to do something useful with that. 10 to the minus 25 seconds. You better get up early. So we'll probably never do anything practical with the Higgs boson. But just like about 100 years ago, when the scientists were working on the electrons and electromagnetic waves, and Faraday, for example, was not one of those scientists, one of those physicists working on the electromagnetic wave. And the equivalent of the Minister of Finance came to visit his lab, and he asked him, what are you going to do with that electromagnetic waves and electricity and all that? So Faraday said, well, I don't know, but I'm sure that you'll find a way to tax us on it. And he's right. We pay taxes now on electricity or on mobile phone, how many electromagnetic waves we get out of that and all that. So, but the reason we do all this work, the prime reason is to increase human knowledge. We want to know what's out there. We want to understand what is this universe that we live in. So that's the main motivation that is behind there for all the scientists. But the main reason that governments pay for it is because it develops technology. And when you develop the technology, you really fuel the economy. Everything that you invest in developing better technological developments, then you, it shows in the economy. CERN, for example, has an office of technology transfer, and everybody who works at the lab is invited to send their best ideas to this office, and they try to find industrial partners to put them into practical use. The third reason why we do it is because that helps training a highly qualified people. And those people go and they work then in all sorts of domains afterwards. And some people go and work in finance, doing all sorts of simulation. Other people work in telecommunications or in medical applications as well. And the other reason, finally, is that it contributes to world peace because we bring people from into large international collaboration. Here you have a group of people, half of them are Pakistanis, and the other ones are Israelis. And those, Pakistan and Israel, are two countries where you don't even have diplomatic relations between them. Those people were put together to build this giant wheel that we saw earlier. And they got to know each other, and they became friends. And then they started doing field trips on the weekends, and they went to visit the Eiffel Tower in Paris and various things like that. So those are things that would never happen if you don't bring people together in a special setting like that. And the benefits are really large. There are immediate benefits for society. The biggest discovery that came from CERN is not the Higgs boson discovery, but the World Wide Web. World Wide Web was invented at CERN because we had scientists, 12,000 scientists from all over the world who needed to exchange information, and nobody wanted to keep carrying large suitcases full of paper. So that's why we created that's why the World Wide Web was created at CERN, was simply to facilitate that. Are the benefits? All those studies by Faraday on electromagnetic waves, for example, now we have, and thanks to all the engineers who were able to put that into action, then we have telecommunications and mobile phones. All the development, all the studies on electrons came the development of electronics. So we have computers and all the electronic devices. Medical imaging, CAT scan, PET scan, X-rays, MRI, all those techniques come from particle physics. All are direct consequences of particle physics. So all the medical imaging. There is one type of therapy that is quite interesting. It was developed here at, first done here at Fermi Lab with the Proton Therapy Center. So the idea is that when you want to zap with X-rays, when someone has a cancer, you want to use X-rays to burn the tumor. But the problem is that when you use X-rays, here are the X-rays, this line here. So here is the amount of energy that is deposited in human tissue and the depth at which they will penetrate. And you see, if I take photons in X-rays, they will deposit a lot of energy all along the way. Imagine that your tumor is somewhere around here. And so it burns a lot of healthy tissue, and it doesn't burn so much of the tumor. On the opposite, if we were to use protons or any particles made of quarks or any hadron, so protons or carbon or things like that, then you can tune it. It's called the Bragg peak here. You can tune your energy such that the particles will deposit all their energy at an exact depth. So if you can tune it like this, and you can deposit a maximum of energy exactly where your tumor is, and you don't burn the healthy cells along the way. So that's a new technique. CERN has been very active lately to develop particle accelerators to produce those proton beams and all that. Here is one it's a center that is now in Italy. That's what the patients see when they go to have hadron therapy treatment. But what they don't see is what is behind the wall is this particle accelerators that was built at CERN, and it's various magnets and a vacuum pipe, and the protons are accelerated there and all that. So that they don't show to the patient. They might be a bit nervous. But that's where they come from. Just about all the best things come from particle physics. So, but have we already found everything? So lots of people, your students and all that, and you're studying to be engineers and all that. Do you think that we will still continue to work in those labs like Fermi Lab or CERN or the others? And the reason is that we know, in fact, very little of what is out there. All the matter that we have studied, that we understand now with the standard model, it only explains 5% of the content of the universe. We now know that 27% of what is all there in the universe is in the form of a type of matter that we don't know at all what it is. It's a type of matter that doesn't emit light, and that's why we call it dark matter. And there is also a very large amount of energy, which is called dark energy, because we don't know what it is, and to go with the dark matter, why not the dark energy? So 68% of the content of the universe. Dark energy, we know it's there because you know that the universe is in expansion since the Big Bang. But what some scientists have realized in 1998 is that not only this is in expansion, but this expansion goes accelerating. Okay, so the expansion of the universe goes accelerating. And they saw that by studying how fast galaxies are moving away from each other. And you know that to accelerate, you need energy. When you're in your car and you want to accelerate it, you give gas. What is accelerating the expansion of the universe? We don't know what it is, but it takes an awful lot of energy to do that, and that's called dark energy. So where we are right now, it's like we have an iceberg, and what is known is just the tip of the iceberg. So the tip of the iceberg is all those particles that I have shown before. This is what we know. All matter that we see that is sending us light from stars and galaxies around us, that is only 5% of the content of the universe, and that we know it's made of those particles. But the rest, we have no clue. So we're far from being at the end of our discoveries. There is a lot that remains to be done. And the best theorists are at work. Here is John Ellis, one of the most famous theorists at CERN, with his assistant, Mademoiselle Mumu. And they're trying to, these theorists are writing papers like crazy, trying to figure out what could be out there, this dark matter in particular, and the dark energy. And last summer, we thought we had seen something. So one way that we look for something new is by looking for something unusual. So the red curve here is what theorists predict that we should find. So we have this accelerator, we have our detectors, we're taking about 200 pictures per second, so various events, collisions that happens. We take all these pictures and we classify them depending on what kind of particles we find in them. So if we look at the distribution of when we find 2 photons, and if we look at the energy of all the 2 photons, and that's the red curve. Theorists tell us it should follow this curve here on a logarithmic scale. And this is the number of events that we should find with 2 photons having this energy. And what we saw, you see the black dots, those are the experimental values that we measured. And you see that there was a little bump, like an excess with respect with what was expected from the theory. So that's what one experiment, Atlas, was seeing in March 2016 after having analyzed all the data taken in 2015. And every year we stop the detector for a few months to do maintenance. And so during that maintenance, we were completing the things. And we had to wait several months to accumulate more data to be able to have an idea. So here we were seeing an excess. But normally, we always have small statistical fluctuations like that. That's normal. What was strange is that the other experiment, the CMS experiment, also found an excess of event exactly at the same value of 750 GeV. And we were all excited, and we started collecting more and more data. And in August, the 2 experiments released their results, and everybody was waiting to see what it was, and in fact, it vanished. There was nothing. Bummer. So, but in the meanwhile, it was so promising. You know, it's that you see one statistical fluctuation that can happen, but for 2 experiments, to have the same fluctuation at the same place, it was just not honest. No, it was sheer bad luck. There was a chance in 100 or 1,000 that it happened, but it did. But in the meantime, theorists are desperate to find what could be there to explain dark matter and all that. And between the first day where it was shown, it was in fact shown in December 2015, and until August 1st so 8 months later, there were 554 theory papers that were written to explain what it could be. And it turned out to be nothing. But it was and there were even some people who could not let go of that hope of finding something new. They kept working, writing papers. But you see, for the first 150 papers, I looked at what was it that people were proposing. And there were all sorts of theories. Most of them were just saying, oh, maybe it's just a new boson, and it would have different properties. So they were trying to to describe their properties. Others were saying, we have some particles of supersymmetry. Others were saying, no, it's something that has to do with dark matter. They had a new gauge symmetry, hidden sector, extra dimensions, heavy or new firm, all sorts of things. Axion, and there were all sorts of strange things that were there. But in the end, nobody knows what it could be. So in this case, nothing was true. But we need an experimental discovery to be able to say what it will be. So theorists are really stuck right now. They're trying to imagine what could it be, this dark matter and all that. But until we have an experimental proof, something concrete, they can all write papers like they want, but we won't be able to sort out which one is true, if any of them. So finding new particles would reveal the secret passage to the bigger theory that would not only explain what we know, but maybe include also dark matter. So here is my take-home message. Ooh la la. Take-home message for this. We can achieve incredible feats building those detectors, finding those tiny particles that are so short-lived and all that. We can achieve all that by getting the best out of highly motivated and diverse people. And diversity is so important because more diversity means more creativity, more different approaches and all that. And it works best when those people are allowed to do as they please, because then they can give the best of themselves. And there will probably never be any applications for the Higgs boson, but fundamental research drives economic development and has completely changed the way we live. Could you imagine going around now without the web, without your cell phone, without your Facebook account? You know, we have changed the way we lived with all this new technology. So, and any new particle, that's for particle physics, any new particle or new phenomenon that we will find from now on will revolutionize the way we understand the universe around us. So I'm going to stop on that. Thank you very much. And sorry, it's been a bit longer than expected.
So, okay, so I'm going to use, you're open for questions?
Yeah.
Okay, so let me use my host prerogative and ask the first question. So you sort of said two things that seem to be not in conflict with each other. You talk about how there were no bosses and how people were able to do, to work and let their creativity get, and yet there wasn't the diversity that you felt there should be. So on one hand, you describe this almost perfect world, but then on the other hand, you say the diversity problem is not fixed. Why do you think it is?
Okay, those are two different things. Like once we're there, it's great, and the way we work, and the way everybody can give their opinion, and everybody can suggest, yes, I have an idea. And we spend our time giving talks and presentation on what we do. And then I may present my idea, and you will say, but did you think of that? And then I will say, oh, no, I hadn't thought of that. And then that will improve my idea. And then you will suggest something else. And you'll say, but I tried that. And that. So you see, once we are there, it's really great. The problem is that getting there. OK? And I'm saying that with more diversity, we would also have better outcomes. Because, like, I was sent to Russia at one point to test my module because they wanted to test it in a nuclear reactor with a flux of neutrons and all that. And my detector had electric connectors at the end there. We had very fancy little connectors with and tiny, tiny screws there, and Teflon and all that, and it was very complex to get it done. And I arrived in Russia, and it was not working, And Russia, it was right after the labs were not well equipped and all that. They didn't have enough support for research at that time and all. And they had assigned an old physicist to be my assistant. The guy was 70-some years old. He was not taking his, he was not retired because then he would not have any money. So he was still good there and all that. And he came every day on his bicycle, and he had a clothespin to keep his pants away from the chain. And I was there trying to fix my things, and they were very fancy. An engineer, American engineer, had spent I don't know how many weeks, months designing those connectors. And was not, I had some channels that were not lighting and all that. So Professor Shafranov came and he said, he took his clothespin and put it on the fancy clamp, and it all worked. So it was wonderful. And so I've seen it so many times that people with different background will approach the problem slightly differently, or they will think of something that they did when they were kids because I don't know what. But it just brings something else, and then we have more chances to find a solution, The American engineers who had designed this fancy thing, he wanted something solid and good-looking and all that, but somehow they were not so well done. So, yeah. Yeah?
So, like 2 weeks ago, my brother sent me this link, some article about dark matter and light matter. Dark is, am I correct? Dark and light matter, and how it interacts with light, or by something like that. And also gravity was also in the mix. So I didn't understand the way they were describing the light and the dark matter. I think how they respond to light, or how they want. Did you hear that?
I'm not sure I understand what the paper was about. So I was telling you that there were 5% of the content of the universe is this type of matter that we know, that when you heat it up, like take any piece of metal, heat it up, and it glows. And so that's what we call visible matter. And then there is dark matter, which is about 27% of the content of the universe. What we know is that dark matter doesn't emit light, so we think that it doesn't interact with electromagnetic forces and photons and all that. But what was the content of the article that you looked at is difficult to guess.
Because I tried to read and understand it. It was so confusing for me. Because they also spoke about gravity and how this discovery could change the way we understood gravity.
Okay, I have an idea. I give you my card with my email. You send me the link. I look at it, and then I give you an answer if it falls in my understanding. It could have been something like that. Yeah. Any other questions? Here. And your name is?
I'm from South Africa.
Ah, okay.
Yeah.
I was there not so long ago. Yeah, I did. We can talk. Okay.
Continue with the black matter.
The dark matter, yeah.
Everything in the universe is attracted by gravity. So therefore, isn't black matter also attracted that you should be able to study it better?
Dark matter produces gravitational fields, and that's why that's how we detect that it's there. We see it, for example, with gravitational lensing, and there are various techniques. But it would be very long to go into all that. But yes, we know that dark matter interacts with gravitational fields. The problem is that a gravitational field is really, really small. And we would like to put our hands on one individual particle of dark matter, put our hands on that, not and that's very difficult because gravity you need a huge amount of matter to produce a gravitational field that you feel. Just to give you an idea, you have some fridge magnets at home? No. So the Earth is a huge amount of matter, and this Earth produces a gravitational field, and it would normally cause your object, your fridge magnet, to fall. And just with a small magnet, you're able to counteract the effect of a whole planet just with a tiny magnet. So you see how much stronger the electromagnetic force, or the magnetic force, is compared to the gravitational force. So with a tiny magnet, you can counteract the effect of the whole Earth. So the problem we have with gravitational effects is that it's extremely small, and it's only when you have huge amounts of matter that we feel the gravitational effect. So we would like to find a way to go and say, yes, here is a particle of dark matter, just like we have other particles, all the particles that I showed you in the things. So knowing that it interacts with gravity is great, but we don't know if it interacts with any of the other forces that I have shown. Electromagnetic force, that's ruled out because we know it doesn't emit light, so it's ruled out. And the strong force is probably ruled out too, because if it was to interact with the strong force, as its name says, it's very strong, so we should have seen that by now. So we hope that it interacts with the weak force, but we have not found that yet. So there are all sorts of experiments that are designed for that. And at Fermilab, no, dark matter they don't have.
No, small one.
There is a small one, okay. There's one, several experiments in Sudbury, in northern Ontario, at Sudbury, the Snow Lab. Very nice things. Also in Italy, at CERN, a few things. So we're trying to find something, but we haven't found it yet.
Gravity does contain the atom, the electrons and the neutrons, who spin around the nucleus of the atom. So the gravity is affecting small.
If you look at one single atom or any of the particles that I showed you, the gravitational fields, they start laughing. You know, it's too small. They're not affected by a gravitational field. On the individual level, it's too tiny. There is just about no effect. It's only when there are huge amounts of matter, like a planet, a star, that then you produce something that we feel. Yeah.
But I tell it,
So I'll tell you what, we want to pick this up after if you two
Yeah.
want to bring it up. So let's thank our speaker.
Thank you all.